Devices and systems convert energy with varying efficiencies, energy forms and transformations. Okay, so we're going to talk about some important things. And one of the driving questions is, what is the scientific definition of work? In order to understand what work means from a scientific point of view, we need to understand what energy is. Because energy is actually the main idea that we're going to be talking about in this little discussion here. So energy is the ability to do work. Okay? So if we look at this cartoon here of the lion, we can see that he's exerting a force on an object and lifting it off the ground a certain distance. He is expending energy to do work because he has lifted an object. Okay? Work is equal to force. He exerted a force and he's lifted that object multiplied by a distance. So work is equal to force times distance. But our discussion has to do with electricity. Okay? So if energy is the ability to do work and electricity is a form of energy, the potential difference, or the voltage, is the ability of a cell to do work. For example, a 9-volt cell will have more potential to do work compared to a 1.5 volt cell because the voltage, or the potential difference, okay, is greater in a 9-volt battery than it is in a 1.5 volt battery. And this term, potential difference, is very important when we start discussing energy transformations. The first law of thermodynamics. This is the basis upon which energy transformations is built upon. Energy cannot be created or destroyed. However, energy can be changed from one kind of energy to another kind of energy. And this has very important consequences for us because we're studying electricity. It means you cannot just make electricity. Okay? Electricity doesn't come out of nowhere. Okay? It's like this with all forms of energy. Because electricity is a form of energy, you cannot make it. That would be contrary to the first law of thermodynamics. So it begs an important question, right? If we cannot make electrical energy, then the important question that follows is, where does electrical energy come from? Where does it come from? Okay? And that is a question that is kind of complicated to answer. And in order for us to come to an answer to that, there has to be a series of lessons that we need to undergo. And it starts right now. So for us to understand energy transformations, we have to take a step forward almost. So I'd like to do just a little bit of classic kinematics. Kinematics is the branch of physics that studies motion, so it's the science of motion. So in this picture here that I got from the internet, we see that there is someone standing on a ledge, and they're holding a ball. So if we look at this ball, we can see that this ball is being held over the ground, right, from here to here, a certain distance given by that variable d. Now, we can see very easily that there is a potential for something to happen here. Something can happen. If she lets go of that ball is going to fall to the ground. Okay? And as it falls to the ground, it falls because of gravity, right? And gravity accelerates that ball faster and faster towards the ground. Okay, so we have two important things happening here. In this scenario, in this first diagram here, we have what's called potential energy. Okay, potential energy. It's written right here. So potential energy just means that an object is in a position where it is about to move. Like, have you ever heard of the phrase, "You got potential, kid"? Right? That means that someone recognizes something special in you, right? Somebody recognizes a talent, a personality trait, a characteristic of sorts that if you just harness it, a lot of really good things can come from you, right? But that's not happening just yet because you have potential for something to happen, right? Just like in this scenario, the ball. So it's the same sort of thing. So that's how you think of potential energy. Potential energy is just a stored form of energy where something is about to happen, where something can happen. And in this case, the potential energy is changed. Okay? It's converted to the next form of energy, which is called kinetic energy. Okay? Why do we call it kinetic energy? Kinetic energy, K-I-N-E-T-I-C, right, occurs because when you drop the ball, or when she drops the ball now moves downwards towards the earth, right, towards the ground, towards the most stable position possible. So we have potential energy being converted into kinetic energy. Okay. Incidentally, I'll introduce this now. There is something else called mechanical energy. So I'll just abbreviate that as E sub M. Energy, mechanical energy, is equal to the potential energy, E sub P, plus the kinetic energy. Okay. So at any one moment in time, we could describe the ball, the energy of the ball in terms of its mechanical energy. Okay. Here we would say that the potential energy is the maximum amount of energy, right? And that it equals the mechanical energy. There's zero kinetic energy here because the ball is not moving. Here, when the ball is dropped, we would say that as the ball is falling, the potential energy is decreasing because the distance between the ball and the earth is decreasing. However, it is accelerating due to the force of gravity, and because of that, the kinetic energy is increasing. Okay? It's important to understand that first law of thermodynamics, that energy cannot be created or destroyed, just transferred from one form to another. Therefore, we could say that the energy in scenario 1 and the energy in scenario 2 are the same. They're constant. Okay? In other words, the mechanical energy in 1 is going to be equal to the mechanical energy in 2, because the sum of the potential energy and the kinetic energy will have to equal that mechanical energy. Now, for our purposes, you need to appreciate that energy is transferred from one form to another. Okay? All right, let's move on. Okay, so a pendulum or a swing, another classic kinematic demonstration where, the person is swinging on a swing, right? They go back and forth, right? And as at different parts of the swing, their energy or their mechanical energy will be described using different things. So when a person is, let's say they're on the backswing, right? There is a small moment in time where they completely stop, right? Because they have to switch directions going back down. At that moment where they stop completely, and you could say that their speed is 0, they have no kinetic energy because they're not moving. So all of their energy, all the mechanical energy, can be described as potential energy. There's potential here, right? And it's just for a brief second, but the potential is that they're going to be swinging back that way. And that's what happens. At this moment in the middle, we notice that their distance from the ground is the shortest. So because that distance is the shortest, and they're actually moving the fastest, the potential energy at that moment in time, right in the middle of the pendulum, is its lowest. However, that means that the kinetic energy is its highest. And going here on the upswing here, or we call that, I don't know, swinging to the right, we'll say that. When it swings to the right, its kinetic energy, that's supposed to say EK, sorry, let me just rewrite that, EK, its kinetic energy is highest, right, or is increasing, sorry, is it going to the right? It's increasing as potential energy is going, let me say that again. Okay, I want to make sure I say that right. As you're going from here to here, the kinetic energy is decreasing, but because the total energy is conserved, that means the potential energy has to be increasing. And again, when it gets here and it stops just for a second, that means its potential energy is at its maximum and its kinetic energy is at 0. So what's the point of all of this? Why are we talking some kinematics? Because we need to understand this. Energy is changing form all the time. Okay? We cannot just create energy. We cannot just create electricity. We need to get that energy from somewhere else to convert it into electricity. Okay? So, here are some examples of energy transformations. So we have a lighter, a light bulb, someone running a marathon, and someone heating up a pan, or sorry, a pot of boiling water. We'll talk more about these in a bit, but these are all examples of everyday devices, right? And then things that we do where there's energy transformations happening all the time. Okay, so you need to understand that there are 4 common types of energy. The first we're going to talk about is what's called chemical energy. Okay, so chemical energy is just the energy stored in chemicals. Okay? This is energy that is released upon chemical reaction. Okay, that's very important what I just said. It is the energy that is released upon chemical reaction. So in other words, if I have a small amount of gasoline, for example, and I just have it, well, nothing's happening, right? In order for me to get anything useful out of it, I have to put that gasoline inside of a combustion chamber, expose it to a spark, and expose it to oxygen so that it combusts, so that it explodes, and then from there, energy is released from that chemical reaction, and that energy is what is used to drive a car, right? You know, to get it to start moving. So this is very important that you understand that the energy is released upon a chemical reactions. That means, right, it is a form of potential energy. Chemical energy is a form of potential energy because the energy is stored inside the chemical bonds that make up that substance. Okay. The next one we've already talked about in the previous slides is called mechanical energy. Oops, mechanical energy. And again, mechanical energy is just the sum of the potential energy plus the sum of the kinetic energy of a system. It is the energy that an object has because it is moving or because it is in a position where it is about to move. The next one we're going to talk about, or you need to know about, is what's called, there we go, the thermal energy. Oh, my printing is terrible. Sorry. The thermal energy is the total kinetic energy, right? So kinetic energy total, right, of all the particles that make up some matter. Okay, so if a particle is moving fast, we would say that it has high kinetic energy. And the last one, can you guess the last one? The last one, of course, is electrical energy. Okay, so electrical energy is just the energy that you find in charged particles. Okay, so charged particles have energy. Okay, and this energy again is known as electric potential energy. Electrical energy is transferred when electrons travel or flow. Okay, so again, when we have a battery, for example, and it has we call the voltage potential difference, well, that's electrical potential energy. But once we take that battery, or I should say the cell, and we hook it up to a circuit, and we give a path for those electrons to go, to travel through, to flow, so to speak, right? Then we have a transference of electrical energy when electrons flow. So those are the four types of energies. Okay, so we talked about this a couple of slides ago, but what are some examples of energy transformations involving those energies, those four kinds of energies we just talked about? Can you think of any devices where energy transformation has to happen in order for that device to work? So in order for you to do this, because this is a skill that you have to do, there are 3 steps that you need to do. The first step you need to do is just identify your device. Okay. The second step is you need to ask yourself a question. What is the input energy of the device? The third question you have to ask yourself is, can you guess? Yep. What is the output energy of the device? Okay. And heads up, there could be more than one possible output of energy. So if you can do that, you can apply this thinking to many devices. So pause the video and think about it for some examples. Okay, so here are some examples. We have a battery-powered toy car and we have an electric kettle. So if you want to pause the video and try to see if you can, come up with the energy transformations, do that now. Okay, so here we go. In the battery-powered car, the energy transformation is as follows. First of all, we have our device. What's our input energy? Well, it says that it's a battery-powered car. So we learned that a battery has stored energy and it uses a paste, right? A chemical paste. So the input is actually chemical energy. And that chemical energy then is converted into electrical energy. Okay, then we have actually one more transformation happening. That electrical energy is then used to turn the wheels of the car, so then we get kinetic energy or mechanical energy. For our purposes, kinetic and mechanical energy are interchangeable. Okay, so you could say kinetic or mechanical. That's fine. Okay, in the kettle, okay, our source of energy, so our input, is going to be, well, right there, it's going to be electrical. And our output is going to be thermal, because that water is going to be heating up. And I don't know if this, I mean, if we want to get really picky, we can hear the water boiling. I don't know if this kettle whistles, but we could say that there is also some sound energy as well. I know that wasn't one of the 4 we talked about, but it is a form of energy. But that's okay. I wouldn't. Electrical to thermal is just fine. Okay, how about you give this a go? What forms of energy transformation is happening in each of these three devices? We have a flashlight, a generator, and a motor. You can pause it and figure it out, or try to. Okay, here we go. In the first picture, the source of energy is going to be a battery, right? Scientifically known as a cell. If we have more than one cell, then that is what's called a battery. And the battery will convert chemical energy to electrical energy, and that electrical energy will be converted to light energy and heat energy as well, because that is what the function or the point is of this flashlight. Our generator takes mechanical energy, the energy of movement, and converts it to electrical energy, because that's what a generator does. A generator produces, well, actually I shouldn't say produce, but it converts some sort of input of energy into electrical energy. Okay, and then we have an electrical motor. An electrical motor will convert electrical energy to mechanical energy, so that electricity coming in will be converted to movement, mechanical energy. Okay, last topic here, very last thing I want to talk about is what's a thermocouple. Okay, so you need to know what a thermocouple is. You need to know what a thermocouple does. A thermocouple is a device that can convert thermal energy to electrical energy, which is really cool. Okay, so it takes heat energy and turns it into electricity. It consists of two different metals joined together that conduct heat at slightly different rates. So you have two heat conductors that one is better at conducting than the other. When the metals are heated, this difference in conduction results in electricity flowing from one metal to the other. The temperature affects the amount of electricity produced, so you can use a thermocouple as a thermometer. Okay, I hope that was helpful, and we'll see you on the next slides.